Hello, everyone. My name is Sean Raymond. I am a researcher. Oh, wait. I guess I'll wait. I'll share my screen in a moment. So I'm a researcher in Bordeaux, a scientific research for the CNRS in Bordeaux. Um, it's a permanent research position, which is quite fun. And I work mainly on a combination of different things related to planets. So I work on solar system formation, exoplanets, small body populations, things like that. And so why don't I share my screen and just kind of get started with what I'm going to say. And so hopefully you can all see my slides now. So what I'm going to talk about today is kind of current thinking about how the solar system formed, but in a kind of zoomed out context, where you take into account the bigger picture of planet formation in terms of how we think exoplanet systems form and kind of what particular pathway the solar system must have kind of followed during its growth to end up how it is today and how that compares with other possibilities. So like I said, my name is Sean Raymond. I'm a researcher in Bordeaux. My blog is planetplanet.net, and everything I'm going to talk about has been done over the last, decade or more with a bunch of collaborators. I've listed a few down here. The kind of key ones are the first two, Andre Isidoro and Alessandro Morbidelli, but many other people have contributed to what I'll talk about. So here, let me get started. So here's kind of a rough outline of what I'll talk about. I'll talk about kind of a thought experiment, what I call the exosolar system. Then we'll talk about super Earth systems, then the solar system, and giant exoplanet systems. And you'll see there'll be kind of a thread connecting all these together and a reason for going in a certain way. So let's get started. So first of all, hopefully you all know and love our own solar system. This is kind of a simple cartoonish view of it, where the sizes of the planets are to scale, but not their orbital distances, of course. And so one way to put the solar system in context is to ask, well, if we were to observe the solar system as an exoplanet with present day Earth technology, what would we see? Which of the planets could we detect as exoplanets? And the answer is if we looked, you know, observed the sun, tried to find our planets as exoplanets, all we could see is this. The solar system would become this exosolar system. The only planet that we could detect reliably is Jupiter. We could detect it with a decades-long radial velocity survey that would measure basically the sun's reflex velocity as Jupiter orbits it. We could measure something about Jupiter's mass, its orbital size, and its orbital shape. And that's it. So our whole solar system would be basically the Sun-Jupiter system. We couldn't see the inner planets because they're too small. And actually, if they were a little closer in, we could see them, but no Earth-sized planets have been found at Earth-like distances yet. And the outer planets, Saturn, Uranus, and Neptune, they're too far away. They take too long to complete an orbit to be able to detect them right now. So with this in mind, like with the solar system becoming the Sun-Jupiter system, we can try to put this in context of what we know right now. And so if we look at the demographics of exoplanets, we can put the solar system in kind of a very rough context. So this is kind of a weird plot, so follow along. So what we're going to do is we're going to start off at the top with sun-like stars. And the thickness of the line will correspond to the relative occurrence of different outcomes. So starting at the top, going down from this kind of star, we can ask a couple questions. So the first question is, well, what fraction of sun-like stars are orbited by Jupiter-like planets? And by Jupiter-like, I mean Jupiter's size or Jupiter mass. And the answer is about 10%. So that's going off to the left here. If you go off to the right, systems that don't have Jupiters, they often have super Earths or sub-Neptunes. About half of all main sequence stars are thought to have these kinds of planets. These are planets, between Earth and Neptune in size that orbit typically closer than Mercury to their star. And some stars have no planets detected yet. Meanwhile, among the planets or among the stars that do have Jupiter-like planets detected, Jupiter mass planets detected, the next question is, well, what fraction of those Jupiter mass or Jupiter sized planets have Jupiter-like orbits? So orbits like our own Jupiters, that is relatively wide and relatively circular. And the answer is, again, about 10%. If you go down here to the left, most Jupiters have orbits that are significantly closer in and often much more eccentric, much more stretched out than our own Jupiters. And so the fraction of, only about 10% of Jupiters that we've found so far have orbits like our own. And so kind of putting these two factors together, the solar system-like systems with Jupiters that are wide and relatively circular, their orbits, they're about 1% of the total. About 1% of sun-like stars have Jupiters. And so for now, since that's all we could detect of the solar system around another star, what we can say is our solar system is kind of a 1% outcome at best. And this is from the only planet out of 8 that we can detect right now. It's possible in the future that we'll find that Mercury's or Earth's or Neptune's are much more common than 1%. But the fact remains that unless demographics change dramatically, the solar system itself can't be more than a 1% outcome. And that's not super rare, but it's not super common either. And so the goal of this talk is to kind of take this sort of plot where we're looking at demographics of observations and explain it with something that comes from planet formation theory. So something about the processes we think that are responsible for forming the planets in the first place and explaining their orbital structures and why our solar system looks one way, whereas many other systems look different. So that's where we're going. So let's get started. The action here is all happening within disks of gas and dust orbiting young stars. Okay? And so we'll spend a lot of time in this talk in kind of cartoon land. And so what you see here is an edge-on view of a gas-dominated disk around a young star. So the first step of planet formation, we think, involves dust growing, sticking together, drifting around, and kind of drifting, getting concentrated. And in certain places, it can become concentrated enough to undergo certain hydrodynamical instabilities. The best known one is called the streaming instability. And this simulation is an animation. Basically, this animation is a simulation of the streaming instability where clumps of dust particles basically become further and further concentrated until in the centers, they have enough mass, enough stuff to gravitationally collapse and directly form what we call planetesimals. So planetesimals are kind of the first macroscopic solids that built the planets. Think of them like asteroids in Star Wars, that kind of thing. They're probably 100-kilometer scale objects. And these are really what we would think of as the building blocks of planets. Now, what's the next step? So imagine in our cartoon disk, planetesimals have formed everywhere. And it's not the case that they must always form smoothly throughout the disk, and we'll talk about that later. But let's imagine that's the case for now. Okay, so you can imagine close into the star where it's hot, the only building blocks you have are solids, and those happen to be refractory things like rock and iron. And so close in, planetesimals are built mostly of rock and iron, and past certain condensation lines like the water condensation line, since there's a lot of water in the disk, going further away than the snow line where water exists as a solid, there's more material to build stuff. And so planetesimals tend to be some mixture of rock and ice. And the next phase of growth is basically, sorry, I should also mention, at the main time, like even though these planetesimals have grown, what they grew from is this dust that drifted around. And you may have heard the term pebbles before. So pebbles is not a very well-defined term, it turns out. So what pebbles really means, or it's basically any dust that gets big enough that it drifts through the gas. We generally call dust when it kind of gets blown around in the wind of the gas disk. And when the dust gets big enough that it sort of decouples from the gas and can drift through the gas, usually ends up drifting inward pretty fast. Those are called pebbles. Right? And so planetesimals are kind of grown out of pebbles. But after planetesimals form, there's still a whole lot of pebbles drifting around. Right? And so the next phase of growth from planetesimals, it can involve big planetesimals grabbing onto pebbles that are drifting around. That process is called pebble accretion. And it's been shown to be really, really efficient in certain places, especially out in the kind of the giant planet region. Pebble accretion is thought to be key for growing the cores of the giant planets. The other process of growth that can happen is planetesimals can just bash into each other and grow by eating each other. And that's generally thought to be kind of the dominant growth mode closer in the rocky part of the disk where terrestrial planets are forming. And what's interesting is that planetesimal accretion is generally much less efficient than pebble accretion when it can operate, right? And so what happens is there's this sort of dichotomy where the rocky parts, where planetesimal accretion is dominant anyway, the growth is much slower. And so for kind of standard parameters of disks, by the time that, Mars mass planetary embryos have formed in the rocky parts of a disk, much larger icy cores have formed further out. And so if you squint at this is kind of reminiscent of the solar system with small rocky planets close in and big gaseous ones further out. So this is kind of a nice setup for how we think the solar system may have formed, but it doesn't always have to be quite this pretty. And yeah, moving along. Let's go and look at our demographics again. Let's go down the branch where giant planets do not form. So what we're going to look at specifically is the formation of super Earth systems. And the occurrence rate of these is probably around 50%, we think, these days. And so this plot shows, a handful of known super Earth systems. This is from 10 years ago now. And so these have been known for a while. These systems are all, each of these systems contains at least 2 planets with sizes between 1, and 4 times Earth's size. And you can see their orbits are, generally much closer than Earth's, right? The x-axis is a logarithmic scale, and the size is the relative size of the different planets. And you can see the solar system at the bottom, right? These colored dots are the, Mercury, Venus, Earth, and Mars. And so how does our solar system compare? Well, it's true, our solar system doesn't have any planets that are as close in as these super Earths. But the distance between any 2 planets is basically a measure of their orbital period ratio. And that turns out to be a really useful discriminant of models. And so you can see that kind of the Earth-Venus separation in period ratio is pretty similar to the period ratios of these super Earths. And so that's not that different, right? Anyhow, it turns out this period ratio thing is pretty useful. So what are we going to use it for? Well, what we do is kind of take this period ratio and make a distribution out of it. So this plot is a plot that shows, just kind of like a curve that doesn't tell you very much, you would think, right? So what this is a cumulative distribution of every time that there's a system with more than 1 super Earth, take the period ratio of 2 neighboring super Earths, you throw it in a bucket, and this is what comes out of the bucket. All right. And so most people look at this and they're like, what the heck is this supposed to tell me? And I kind of feel the same way. So the way I frame this is this distribution doesn't really tell you that much in terms of what it looks like. What it tells you, what's interesting, about it is what it doesn't look like. So it does not look like what a lot of people predicted it should look like, which is this. A lot of people thought this would look like a staircase. So why would this be a staircase? It's because certain period ratios correspond to what we call orbital resonances. So the 2-to-1 resonance, for example, that's where the outer planet makes 1 orbit and the inner planet makes 2, and the 2 planets realign, right? Or the 3-to-2, and the same thing with different ratios of periods. So orbital resonances are thought to be kind of a signature of orbital migration. And a lot of people predicted that orbital migration was going to be the dominant process to explain the presence of super Earth type planets very close into their stars. Yet the period ratio distribution did not look like a staircase. So what does this all mean? Well, let's look at this a little bit more closely. So I'm going to argue from the start that even though there's not this staircase function, all roads lead to migration. You can't avoid it. It's really just inevitable. And so what is this migration thing? This plot shows a snapshot of a hydrodynamical simulation. In this case, there are 5 different planets within a gas disk. So each of those little concentrations things is a planet. And they're each migrating within this disk. And what is migration anyway? Basically, migration is a gravitational interaction between growing planets and the gas disk. And each of these spiral features that you see, those are density perturbations to the gas disk caused by the presence of the planets. And those spiral density perturbations act to torque the planet's orbits, and they cause them to either shrink or grow, usually to shrink, but not always. And so basically this process of planets' orbits interacting with the gas disk and usually shrinking is called orbital migration. The key thing you need to know is this process is pretty universal. We don't think it's avoidable. There's still some debates about the details of certain aspects of it, but it's not really avoidable. You can't just pretend migration doesn't exist. And migration seems to be faster for more massive planets. And one final detail that's really important in terms of super Earths is that it appears that disks have inner edges. So models and observations both show this pretty much universally. So that disks don't go and touch the surfaces of stars, except maybe very rarely during outbursts, but not for long periods of time. And so disks have these inner edges that you see here. And what does that mean? It means that since the disk is driving the migration, basically migration stops at the inner edge. So this planet that's migrating inward will be stopped at the inner edge of the disk. Right? The planet cannot just migrate and fall onto the star. Okay. So putting all that together, let me explain kind of the current thinking of our model for how super-Earths get there. Now, starting from this disk of kind of planetary embryos, and I'm going to show it to you in cartoon form again, even though there's a zillion simulations that demonstrate exactly how this works. The cartoons I find are a bit more intuitive. But here's how it works, right? A bunch of planetary embryos and planetesimals are within a gas disk, and then some of them get big enough, grow big enough, fast enough to migrate. So what happens is something like this. They start migrating inward. They plow into each other. Sometimes there's collisions, but the planets kind of keep migrating inward. But they're all kind of getting squished because they're migrating inward, but they don't all get squished into one planet. They tend to end up in chains of orbital resonances, where the innermost planets are anchored at the inner edge of the disk. And so these are kind of characteristic resonances that I'm throwing in there. And so this is nice, right? So this happens universally. Sometimes these chains break. But while the gas is still there, then the planets just settle back down, and then they reform a new chain. And so in these chains of orbital resonances, each pair of neighboring planets is in resonance. But is this kind of situation stable forever? I like to describe this as being, the key factor here is the gas disk. And I like to describe the gas disk in this context anyway, as being kind of like the teacher in a classroom, at least a good teacher, right? And so the teacher is kind of keeping the kids in line, keeping everyone doing what they're supposed to. But when the teacher leaves the room, the kids can go bonkers. And so what happens in disks and in our simulations is that when the gas disk dissipates after a few million years, usually these systems of resonance go unstable. There's a phase of collisions, and planets' orbits spread out, and the resonances are gone. Okay. And so put together, let's look again at this period ratio distribution thing. So now I'm going to plot some simulations on top of it. In red, those are simulations at the end of the gas disk phase. So while systems are indeed in these nice resonant chains, and that's why it's making them basically a staircase pattern. Then what happens is the gas disk goes away, the systems go unstable, they spread out. And so their distribution moves to larger orbital period ratio. That's the blue curve, right? And so in some sense, in very simple terms, if you mix the blue curve and the red curve together, you can get the observations, which is the gray curve in the middle. And there's plenty of details in there to do it properly. But the punchline is basically about 95 to 99, more like 98 or 99% of systems of these resonant chain systems have to go unstable to match observations. And if they do, we can match the observations really nicely. And so that's really nice, right? This works really well to explain it. Maybe all super Earth systems go through this phase of resonant chains, and we just only see the ones, basically what we see is the survivors after those things go unstable. Of course, the coolest systems that we know are the ones that remain and are observed in resonant chains, like the TRAPPIST-1 system, which has 7 planets in a chain of resonances, right? These kind of systems where you can see many, many planets in resonance are amazing, right? They're cool, and they're also really valuable scientifically for several reasons. You can use them to get really good estimates of the planet's masses. You can use them to really understand very careful the exact migration histories of the planets. And you can even use them to constrain the bombardment histories of these planets and compare them with the planets in the solar system. So let me explain that last point really quickly. It comes from the fact that these resonant chains are basically fragile. So what do I mean by that? Well, let me explain a very simple numerical experiment that we did to kind of demonstrate this. So what we did is we started with the TRAPPIST-1 system, all right, with the best fit of the TRAPPIST-1 system. And we tried to see what it would take to break it, right? And so basically we threw in a few extra bodies. We did 2 kind of key cases, imagining there's one kind of leftover rogue planet or 1,000 leftover rogue smaller bodies, planetesimals, right? And we just wanted to see kind of, what it takes to break the system. And the reason we want to find that out is because the system excuse me, the system right now is not broken, right? It's still in a resonant chain. So if we find out the kind of minimum perturbation it takes to break it, that's basically an upper limit on what could have happened in the past. We can't pinpoint exactly what happened in the past, but we can put an upper limit on the bombardment that must have taken place. And so here's the outcome of one of these simulations, or one of these kind of experiments. So what you're looking at here is on the y-axis, the time for a system to go unstable as a function of the mass of a single rogue planet that we injected into the simulations. And so there's three different kinds of outcomes that I'll just put here. So the black points are where the system was shaken up so badly that there was collisions between the planets. And so that's really what an instability happened, right? In red, those are systems where the system spread out and lost the resonances. The system didn't go unstable, but the resonances were lost, okay? And the resonances are measured by these resonant angles. And so when resonant angles stay nice and confined, as you see in the blue, basically in that blue square in the top left, that means the system stays in resonance. And the red ones, you can see the resonances are lost. Okay. And so what we can see from this plot is the more massive this rogue planet, the more likely it is for the system to be disrupted. And basically the most massive, or sorry, what is it? The least, basically the most massive one that survives is about the mass of the moon. Right? So the biggest impact that could have taken place on any of the planets is about a lunar mass impactor. Anything bigger than that would have disrupted the resonances that we see today. And the most, we figured out the most likely planets to have been collided with and so on. The other way of doing this is with this swarm of small bodies, planetesimals, and the outcome is basically the same. Here's the same color coding where blue means the system kind of remained in this nice resonant state as we see it today. Red means that the system spread out beyond the resonances, so it's not consistent with what we see today. And the black ones are, collisions, so it's bad. And so again, the furthest, the highest mass in terms of the total mass of this swarm of planetesimals that maintains the resonant structure that we see today is about, 5% of an Earth mass in planetesimals. And if that was the case, then we can figure out from those simulations what happened to those planetesimals because they bashed down onto the planets. And so we can figure out basically which planet was hit by how much stuff. And that gives us an upper limit on the bombardment history for each planet. And the numbers are listed in this table here. So for each of the planets, B through H, this is the orbital distance, and then kind of the maximum mass that they could have been bombarded with after their formation, right? So time zero here is basically after the gas disk disappeared, which is kind of the last time that after the resonant chain was put in place. And what you can see is that for all of the inner planets, they could not have been hit by even as much as Earth, right? The upper limits are less than Earth's late accretion. Late accretion on Earth is all the mass that was bashed into the Earth in planetesimals after the moon forming impact. And it was about 0.5% of an Earth mass. And so here we have constraints that are about on the same level for a system that's 40 light years away, thanks to these resonances. So that kind of just illustrates the power of these resonances and how cool they are, even though they get disrupted most of the time. And so another kind of little punchline is that since there's so little late accretion, the planets must have formed fast, which makes sense. All right, let's move along. So now let's go to parts of the diagram where giant planets do form, and they actually do end up on solar system-like scenarios with wide orbit giant planets like Jupiter. And of course, we'll use the solar system itself. So let's look at how the solar system itself formed. So what we're going to do is look at different models for how the solar system could have formed. And we're going to focus on reproducing the inner parts of the solar system, kind of interior to Jupiter. And so what exactly are we trying to reproduce here? So here's our constraints. The terrestrial planets contain in total about 2 Earth masses of stuff. The asteroid belt is very important, but it contains almost nothing. It contains less than 1,000th of an Earth mass. But there's still millions of asteroids that are actually cataloged now. And they do have a decent amount of, substructure. And it's important to be able to kind of match in broad strokes what we see in the asteroid belt. So among the terrestrial planets, we want to reproduce kind of these sorts of quantities, like the numbers and masses of planets and their orbits. And for the asteroids, we want to reproduce kind of their very low mass and the rough dichotomy in compositions that we see and their orbits. Okay. So here's the a simulation of the classical model. So this model was developed by George Weatherall and others over the span of a few decades. And the key assumption here is that you can treat giant planet formation and terrestrial planet formation completely separately. So time zero here is right when the gas disk disappeared. We assume that Jupiter had already formed, but that Earth and the rocky planets have not finished their growth. And so there's just kind of a smooth disk of planetesimals and planetary embryos. That's what you see in terms of the green, red, green, and blue objects. And so I'm just going to let this go and we'll see what happens. So kind of the planetary embryos there's a wave of growth that sort of sweeps outward from the inside. And then there's a bunch of stuff that gets excited from the outside in by Jupiter. And right around 1 AU now, you can already see a pretty good Earth analog. And you can see it's red, which means it's very dry. And its color changes slowly as its feeding zone expands to include objects that started with different compositions. So by this point, most of the growth is done. And you can see that there's a kind of a clearing out phase where leftover stuff is thrown out of the system. And by now it's basically over. You can kind of squint and say, okay, well, there's some decent, there's a pretty good analog of Earth and Venus in there. And then there's Mars and the asteroids. It's good. We solved it. The problem comes when you look a little bit more closely. The key problem is that Mars is systematically the wrong size. So in this case, Mars is about 5 times too massive. Earth and Venus are decent analogs, but Mars is too massive, and Mars is systematically too massive. And we call it the small Mars problem. And George Weatherall was actually aware of this and wrote a paper about it back in 1991. And so this really shoots down the classical model quite dramatically. It's really crazy how it's very, very hard to match the small Mars problem, within the context of this classical model. And so to date, there are at least 5 solutions to the small Mars problem that have been proposed. And so I'll go through them kind of one at a time, just briefly describe them. So one, and I've ordered them here in terms of when the key action happens. All right, so they each have kind of specific processes that are central to explaining why the solar system looks the way it does. And so they happen at different times. And so we'll go through them in that order. So the first one's called the empty primordial asteroid belt, then pebble-driven model, convergent migration, grand tack, and early instability. So let's jump into this empty primordial asteroid belt model. So this model is kind of weird when you first hear about it. The assumption here is that few or maybe no planetesimals ever formed in the asteroid belt. And so the reason there's 2 Earth masses of material, in the terrestrial planets, and then there's giant planets further out, is because that's where a lot of the stuff formed, the macroscopic stuff, the planetesimals, the planetary embryos, and so on. But in the asteroid belt, there's so little mass because nothing ever formed there. All right. So this seems weird. Why would this ever happen? And this seems weird until you look at recent images of disks around other stars. And what we're looking at here is images with ALMA, a submillimeter telescope, a radio telescope, that's looking at basically pebbles. It's looking at kind of millimeter-sized dust grains within disks. So this is actually, it's looking at the building blocks of planetesimals. And you see these dark rings and you see bright rings. And so it's easy to imagine that in the bright rings there, that's where the streaming instability is happening, planetesimals are forming. But in the dark rings, there's a kind of a lower density of pebbles, and so you're not getting planetesimal formation. So maybe planetesimals actually form in rings. And there's several models that have come out in the last 5 years or so showing that planetesimals may actually form in rings instead of in disks. So this plot shows the outcome of one model from Isidoro et al., in which 3 different rings formed. So one ring that's centered around 1 AU or so, that can, in this case, contain about 2.5 Earth masses. Then a central ring kind of centered around Jupiter and Saturn's orbits that contains much more like 85 Earth masses. And then an outer ring out at 20 to 40 AU or so that contained 18 Earth masses in this case, right? That's just one example that was chosen because it looks a lot like the solar system. but maybe planetesimals actually form in rings. And the asteroid belt was kind of between the rings. So if that was the case, then, and these really are the initial conditions for how the solar system formed, then what happens next, again in cartoon form, is something like this. Basically, Mercury and Mars would be small because they would have been scattered out of the ring. So their growth was kind of stunted, whereas Venus and Earth grew big because they were right in where most of the mass was in the center of the ring. And there you go. It actually matches the terrestrial planet's orbits really well. When you simulate this process, it's very surprising, but it works really well. But then you could say, well, what about the asteroid belt? It's not actually completely empty. It can't have really started with nothing. And that is a problem that I spent about a year trying to figure out a few years ago. And the answer turns out to be that the asteroid belt is this big kind of empty piece of real estate. And there's no way that it can just stay empty. Basically, as the giant planets form, they naturally dump anything that's nearby. Some fraction of it gets dumped into the asteroid belt, preferentially in the outer part of the asteroid belt, where the C types are. Meanwhile, terrestrial planet formation does the same thing. It scatters planetesimals all over the place, and some fraction gets implanted into the asteroid belt from the inside. And these processes are not super efficient, especially scattering out from the inside. But that's good because the asteroid belt's almost empty anyway. We don't think they should be efficient. And so it turns out that you can actually reproduce the asteroid belt perfectly well, starting from 0 planetesimals ever forming there, and that they're entirely a story of implantation. And it works really well. And so that whole story holds together pretty well. Now let's move along to the second scenario. The second scenario is this pebble accretion model. And this model is kind of the most controversial of them right now, but I think it's worth considering and discussing anyway. So the pebble accretion model kind of goes against the grain in some sense and proposes that pebble accretion is still kind of a key growth mechanism for the terrestrial planets, not just planetesimal accretion. So it proposes that planetesimals form kind of in a preferential location, and then they grow by grabbing onto pebbles, and as they grow, they migrate inward a little bit. And so planetesimals form kind of there, and basically they move a little bit and they grow. Then maybe there's a second generation of planetesimals, and that happens again, and it happens again. And then there's only a limited number of these events, but you get a limited number of planetary embryos that are kind of the building blocks of the terrestrial planets. And they have kind of a size order where the ones that are furthest away from where they started off are the most massive. And Mercury has to form slightly differently in this model. Fair enough. Then the gas disk would have gone away, and there would have been a final collision between 2 of these to form the Earth-Moon system. And so that's the story, and it fits together relatively well. There's still plenty of debate about whether this is really self-consistent and whether it matches meteorites and stuff. But I think it's worth including in the discussion, and it's an interesting different model. The next model is the convergent migration model. And so what this model proposes is that planetary embryos, as they grow, they migrate around, which is kind of to be expected, just like super Earths do, or their building blocks of super Earths do. But what's different is that this model kind of relies on certain disk models that have come out recently showing that in the inner parts of disks, in certain cases, migration can be outward. And so if there's outward migration here, inward migration here, outward migration there, whichever, then there's certain zones where migration is convergent. And so things migrate towards a given zone. And so if the convergent migration zone happened to be around Venus or Earth's orbit, basically that has the same effect as if planetesimals really formed in a ring, because planetary embryos grow wherever, but then they migrate convergently to create a ring. And so that model is kind of illustrated in this cartoon here. And it works really well also in terms of getting most of the mass within a narrow radial zone, like what we see in the terrestrial planets now. And it matches their orbits pretty well. So it's another possible mechanism. The key uncertainty is whether this migration really is convergent in the right place at the right time and lasts long enough. So this one has kind of a big if to it. But if that's the case, it works great. The next model is kind of the best known of these because it was the first one to be developed. It was called the Grand TAC, it relies on the migration of Jupiter and Saturn. And so the key kind of thing here is it invokes this certain migration history for Jupiter, which probably seemed quite generic at the time when we came up with this idea anyway. So the idea being that, this, what we're looking at here is kind of one of these simple diagrams with no units on the axes, showing kind of a cartoon scenario for Jupiter's growth. Grew, got big, it got piled a bunch of gas onto its core and started migrating inward. It cleared out a gap. It migrated inward and would kept going inward if not for Saturn. The fact that Saturn was doing the same thing. Saturn did the same thing, but further out, a little later, migrated inward, caught up to Jupiter. Just like for super Earths, it doesn't mean that it collided with Jupiter. It got caught in resonance, either 3-2 or 2-1 resonance, according to simulations. And for certain conditions, the two planets can actually migrate outward. And so this is the assumption of the grand tack model, that there was this inward, then outward migration phase for Jupiter specifically, and that the turnaround point was around Mars's orbit. Because if it was around Mars's orbit, then it can basically create a ring out of a disk. And so this simulation shows that. What you see is a bunch of planetary embryos and planetesimals, and then they're getting bulldozed by Jupiter that migrates inward and then turns around, goes back outward, and squishes everything into a ring from a disk. And so it creates this ring of planetesimals and planetary embryos, just like convergent migration does, just like if planetesimals form in a ring, we already start with that. So that's why the grand tack model works, and it works really well. If that migration is really how it works, right? If Jupiter really could have migrated inward and then outward quite a long ways. The next and final model, which I think is misnumbered, I think we're on number 5 here. It relies on the dynamical instability of the solar system. That's sometimes called the Nice model. And the Nice model is invoked because it explains a bunch of different things in the solar system within one kind of event. So the idea here is that we think that the solar system started off looking a little bit different than it does today. All signs point to the giant planets forming kind of like super Earths and ending up in a chain of orbital resonances, and their orbits are not resonant now. So we think that they did kind of a similar path as the super Earths, where they got in resonance and then they got out of resonance. And the way they got out of resonance is this instability. So that what it looks like is something like this. Here, all the green dots are outer planetesimals. Let me pause it for a second. So the green dots here is an outer disk of primordial planetesimals. So kind of like the early Kuiper belt, or where all these green dots are basically early comets. And what happens is the circles there are the orbits of Jupiter, Saturn, Uranus, Neptune, and an extra ice giant that's not going to survive. So the instability, boom, it happened there. And an extra ice giant was ejected. That caused the planet's orbits to all spread out quite a bit. And then they reached their current final orbits. Okay. And so this instability is really nice because it can explain the giant planet's orbits, it can explain a bunch of small body populations like it can explain the Trojans of Jupiter, it can explain the irregular satellites, it can explain the Kuiper belt, parts of the asteroid belt. It can explain a whole lot of stuff. Oh yeah, I guess I forgot. I had this plot to explain all that. So it can explain the giant planet's orbits, the inclination of Jupiter's Trojans, the capture of irregular satellites, the orbital structure of the Kuiper belt, and more. It's really a very successful model. It can explain a lot of stuff, right? So the giant planets seem to have had this instability that tossed around a whole bunch of these early planetesimals, and many of which we see today on these certain orbits that are kind of like frozen in time, telling us something about what happened in the past. And the key question here is, well, when did this happen? When did the giant planets go unstable? And this all kind of rests on information about the moon, because initially it was all tied to the moon. And so the key thing about the moon is we can't reconstruct the bombardment history of the Earth because of erosion, and the impacts that happened early on Earth are completely buried by plate tectonics and erosion. It's very hard to reconstruct what happened on Earth. The moon is a much more pristine, and so we can look to the moon and try to reconstruct its past, impact history, and use that to learn about Earth's past impact history. So this plot is just showing where samples have been, basically where landers have landed on the moon and where samples have been taken from the moon. And so they've been taken from the moon specifically even by people going there and bringing them back, the Apollo samples, of course. And so by doing that, taking rocks from the surface of the moon, age dating them and trying to figure out a distribution of impacts, there's been a debate about this that's been going on for 50 years now. And so starting in 1974, the key model that came out there was called the cataclysm model. So that's this model that declines really quickly, then it's pretty low, and then there's a spike. And that spike is called the cataclysm. It's often called, in common terms, the late heavy bombardment, but it's really the cataclysm model. All right. And so there's been this kind of debate between the cataclysm or a more smooth decline for a long time. And this cataclysm idea basically means that if there was really a spike in bombardment right then that's kind of when the giant planets would have been going unstable. And so the original timing of this instability was basically tailored to be that spike. And so in the original Nice model paper, that's when the giant planets went unstable. That's when everything was bashing into the Earth. But the problem is that reanalysis of the basically all of craters on the moon and different time scales and different timing methods have shown that this is probably due to sampling bias. And so this spike at 3.9 gigayears ago is the age of the Imbrium basin. And that event probably contaminated a lot of different parts of the moon's surface and led us to think that was basically a global thing rather than a one individual event. That's the current interpretation of what's going on. And so it's generally agreed upon now that this cataclysm was not real and it's sampling bias. And what really happened is more as a smooth decline. And there was a late heavy bombardment because the Imbrium impact did happen, but it was one impact, not a bazillion bashing into the planets. So when did the instability actually happen? Well, it seemed to have happened earlier than about 100 million years after the start of solar system formation. Exactly when? It comes from different constraints. And there's even some recent constraints that suggest that it happened really fast, like within 10 million years or so after the start of planet formation. And it's still kind of debated, but it happened early anyway. And if it happened early enough, it could have affected the growth of the terrestrial planets. That's why it's coming in when I'm talking about terrestrial planet formation. And so that's what's called the early instability model, and we'll talk about it in a sec. One possible trigger for the instability is actually the gas disk dissipating in itself. If the gas disk dissipated, kind of like you see in this cartoon, where high energy photons from the central star kind of dig a hole in the disk, and then the outer parts of the disk are like a donut that just expands until it goes away, that can actually affect the planets. The reason it can affect the planets is because this inner edge of the outer disk, kind of the inner edge of that outer blue part, that is like the inner edge of the disk in the super Earth scenario where it stops migration. So everything out in that blue area can migrate around, planets out there can migrate. As the gas gets less dense, they migrate slower. But this edge kind of is an anchor point and can push planets around. And so here's an illustration of that. This is in the case of the inner edge of the disk, but it's analogous. And so what you see here is in this animation, a planet migrates inward, but then the inner edge is getting pushed outward and the planet follows it. And so that same thing can happen for the giant planets. So now this plot shows that dashed line is the evolution of the inner edge of the outer part of the disk as the disk photo evaporates. It kind of hops over Jupiter because Jupiter is so massive that it has already cleared out all the gas that's nearby anyway. But it manages to push Saturn out a little bit and squishes Saturn against the ice giants and causes the instability. And so one possible trigger for the instability, the Nice model instability, is the gas disk dissipating. So that would have been a very early case. There's also the possibility that the instability can just happen naturally after the disk goes away. And so this is a nice plot showing the kind of two-phase thing. This early part of the plot is a simulation, a hydrodynamical simulation showing the growth of Jupiter, Saturn, and 3 ice giants. Then the dispersal of the disk, and after the disk is gone, the giant planets go unstable on their own. That can happen also. Regardless, it's pretty plausible that the instability happened pretty fast. And if that was the case, it would have affected the growth of the terrestrial planets. So here's a simulation of the growth of the terrestrial planets as influenced by an early instability among the giant planets' orbits. And what you can see is that basically the instability is triggered after 1 million years, and it really strongly clears out the asteroid belt, which in this case is not depleted from the start. And the final state of the system is not perfect, but the kind of Earth-Mars mass ratio is pretty close to the real one. And on a distribution level, this model matches the solar system's terrestrial planets really well. So we have these different, 5 different scenarios right now for forming the terrestrial planets. And there's some key questions that need to be addressed to really figure out which of these can make sense. So I'm conscious that I'm getting low on time, so let me go quickly through the final part of this diagram. So this bottom left part about giant planet when Jupiters form in non-Jupiter-like scenarios. So if we look at the giant exoplanets, only a small fraction look like our own Jupiters, as we saw, right? So this is the orbital eccentricity distribution as a function of orbital separation. I drew Jupiter on here for scale, and you can see most gas giants have much more eccentric orbits. And we think there's 2 key processes responsible for this. There's migration that brings planets inward, and there's scattering or instability that moves planets up in this diagram. So instabilities like this are the same kind of thing that we just saw for the giant planet instability of the solar system, but in a more general sense, they can be much more violent. So here's what that can look like. In this animation by Eric Ford, there's 3 planets around a star, and the outer 2 have been kind of jostling each other such that their orbits start to cross, which means they can be in the same place at the same time, but it doesn't mean they have to collide. Rather, they have this kind of series of close gravitational encounters where there's exchanges of orbital energy, and finally there's a big enough kick that one of the planets gets launched out of the system and ejected into interstellar space, never to come back, right? And the surviving planet has this eccentric orbit, and that eccentric orbit is basically kind of a scar from this violent past. And in terms of, giant planets probably don't form alone. So here's a simulation where there's 3 giant planets, kind of a Jupiter and 2 Saturns. And there's also this inner part, which is a bunch of rocky stuff forming rocky planets, and an outer disk of kind of comet-like planetesimals that are, just sitting there getting ground away. And then the movie slows down for some reason, and then boom, right? So what happened there is a dynamical instability happened. In this case, it was a little delayed, and I chose that to build the suspense, of course. But in case it was a little delayed, but what happened is the giant planets went unstable and they affect everything else. They're so massive that they dominate the gravitation of the system and they affect everything else in their system. So in that case, most of the rocky stuff got dumped on the star. A few rocky planetary embers were ejected. Most of it got dumped on the star. All of those outer comets were ejected. And basically, we turned a system that looked kind of like the solar system into one that looks a lot more like many exoplanet systems. And in the process, destroyed all of the nice rocky planets. It's a bummer. Of course, all of those comets, outer planetesimals were ejected into interstellar space, right? As was one planet. And these days, we regularly find free-floating planets that don't have any stars. So here's one, this diagram is showing from one specific star-forming region called Upper Scorpius, where about 100 free-floating planets were found in one region. And that's enough in one spot to try to figure out details about where they came from, whether, what fraction of them are ejected planets and what fraction of them are maybe failed stars. And that's the kind of analysis that we can do now, because with new telescopes like James Webb, we can look and find a whole bunch of these at once. Meanwhile, we are also finding interstellar objects, some of which are probably planetesimals ejected from planetary systems. That's the trajectories of Oumuamua and Borisov as they flew through the solar system. Right? And new missions such as Comet Interceptor may help characterizing the next interstellar objects. And so I'm going to stop there. If you want to know more about this stuff, this review paper that has the same title as the talk contains a lot of what I talked about. And I also have a blog on which I wrote a whole series about solar system formation that I call the Solar System Story. And so you can get a lot of stuff on there too. So thank you very much. I'll stop there.
Thanks a lot, Sean, for this first seminar in 2025. And I would then, as usual, ask for questions and discussion contributions. You can either raise your hand, or you can also, if you wish, which put the screen on so that I can see you and wave at me, then you can actually I can actually see you. But the best is that you raise your hand in the dialog box. So the floor is now open for discussions.
I see one hand up. Claudia.
Yeah, let me see. Yes, yes, yes. Claudia Dante, please.
Hi, I'm Claudia from Copenhagen University. I was wondering, when you first mentioned the first model that you used to explain the formation of the solar system when you have already a Jupiter that you say you form through pebble accretion, and then you have a bunch of inner embryos that go through planetesimal accretion. I was wondering, since you have already a bunch of pebbles which allow you to form a Jupiter, how is it possible that you get to the point that you have a Jupiter and you don't have any other inner embryo already with a relevant mass?
Oh, I mean that. So that's a good question. So why would you ever end up with Jupiter being kind of the such a massive thing without anything really big
With
closer
yeah,
in?
without anything else in the inner part of your disk.
So the truth is that that's kind of an unsolved problem in some sense. And it may be that the solar system's case is a little different than the average. So there's several papers showing that one thing that we actually predicted about 10 years ago is that we predicted that there should be an anti-correlation between systems of super Earths and systems with outer Jupiters. And our argument was that Jupiters would form and kind of block the migration of planetary embryos. And it turns out there's been a bunch of observations to test this idea. And they found that not only were we wrong about this, it's the exact opposite. So
Yes.
it turns out there's correlation. So systems with super Earths are much more likely to have outer giant planets. And so in that sense, it kind of goes along with what you'd expect, where when, imagine a whole train of planetary embryos forming, some of, one of them is going to become a Jupiter, others may migrate past Jupiter and become super Earths. That kind of thing kind of fits in terms of a general scenario. But how do we avoid it in the solar system? And so the
Yeah.
solar system, so first of all, of course, we don't know for sure exactly why, but it's possible that Jupiter just happened to be the innermost kind of big one and formed fast. So if there is kind of a group of planetary embryos out there and the innermost one grows fast enough, then it can basically block the pebble flux towards the inner part of the solar system. I didn't talk about this, but once a core gets bigger than 10 or 20 Earth masses, it can block the pebble flux towards the inner parts of the solar system, of the planetary system. And so then you kind of cut off growth of anything closer in. And it also stops the migration of anything bigger further out. And so for this to happen, you'd need to have, no really big reservoir planetesimals closer in. And so if planetesimals form in rings, for example, the inner ring cannot have had 20 Earth masses. It could only have a few to avoid getting really big on its own. And then also Jupiter would have had to form relatively fast and block the flux of pebbles. And so basically there's several different things that would have had to happen. And also Jupiter had to be the innermost one of those large outer planetary embryos. So if each
Yeah.
of those is met, then you can understand why it happened. Otherwise, you need to come up with some other idea.
And how likely you think it would be to not have like any planetesimal ring in the inner part and having this Jupiter core to be the innermost planet? Do you have like
Ah,
any?
so it's not that you need no planetesimal ring at all. It's just that it has to be below a critical mass to get massive enough on its own to form supernova. So if the solar system's like kind of imagine the solar system formed from these two rings. If the inner ring was more than I think about 6 Earth masses, or maybe it's less. I forget the number. There's a number on this from a recent paper by Shibata and Isidora. But if it's more than some number of Earth masses, that's not very much more than we have. I think it's 4 or 6. Then basically the terrestrial planets would have grown fast and migrated inward to become super Earths anyway. And so it's not that you need zero planetesimals to form. It's just there's a certain threshold, and we're below that threshold. And why are we below that threshold? That might even go back in the clock and go to details of what the sun's disk looked like or some other process. But these are great questions, and we want to find the answers. And so, very good question.
Okay, thanks.
There is a question from Bill Irwin via the chat. Is there a planet 9?
Oh, so is there a planet nine? No one knows. It's been proposed to be out there. I think LSST, the Vera Rubin telescope will be online very soon. I know they're already taking commissioning data. And that telescope will have a higher than 50% chance of finding Planet 9 if it exists. So within a few years, we'll know if it exists or not. Either it'll be found in the next few years or no one will believe it exists anymore. So then there's a question of how it could have got there. We have a new paper about this. One possible way it could have got there is actually either during the formation of the ice giants or during the giant planet instability. There's large objects like extra ice giant kind of mass objects that get ejected. But they don't just kind of, they don't, what happens during an ejection is a planet gets ejected, gets kicked out, it gets kicked out further and further. And so in isolation, that leads to ejection, and that's it. However, if you take into account the fact that the sun was born in a cluster with many other stars, probably a few thousand stars, what happens is as a planet's getting ejected, there's some time window where it can get perturbed from the outside by other stars as they fly by. And so the odds of any given, if you take that into account, the odds of any ejected planet being captured onto a wide orbit, kind of similar to the one that Planet 9 is proposed to be on, the odds are maybe 5 or 10%. And so during the formation of the ice giants and the giant planet instability, we think there were probably 4 or 5, 5 to 10 Earth mass things ejected. And so if you put that all together, it's something like a 30 or 40% chance of one being captured on an orbit like Planet 9's. So that's kind of where I think it would have had to come from if it exists.
Next question is by Priyanka, please.
Hi. So sorry about not turning on my video. It's kind of night here and I look really weird. Yeah. So I was just thinking about the Nice model that you explained about, and then about how the evaporation of the gas disk could have led to the disk instability. Now the thing is, I remember reading about planet formation in general, and it suggested that planetary migration inwards due to loss of angular momentum as a result of friction was expected to happen. I don't know if this is an outdated idea or if this is just one of the possibilities, but if such an inward migration is considered common or expected, then for the Nice model to happen, would we expect that the inward migration just did not happen initially?
No, so we think inward migration had to happen. Migration is kind of unavoidable. What is uncertain is the details of migration in terms of exactly how fast it is. And so migration must have happened to some degree. Now we know empirically that Jupiter is not a hot Jupiter, right? So Jupiter didn't migrate all the way in. So why is Jupiter where it is now, right? It must have moved around because if it's made out of gas, we know that gas, the interactions between planets and gas disks cause planets' orbits to move around, right? They shrink, sometimes they grow. And so that was happening. It had to happen, right? And so the question then becomes, well, what are the plausible evolutionary paths that could have led to Jupiter being where it is now? And the Grand Tack is one extreme case where it went really far inward and then back outward. There's other cases that are pretty extreme where Jupiter must have formed really far away and migrated inward. And currently things are kind of converging on a scenario where the viscosity in the disk may have been much lower than previously assumed. And there's several constraints that kind of point in that direction. And if that's the case, then migration still happens, but it's slower. And so in some cases, it makes this kind of thing easier because Jupiter would not have migrated as much or as quickly. And so then there still would have been migration, but Jupiter would not have gone as far. And so it's not as hard to explain why it is where it is now. And so given that, all right, so given migration, it makes sense why Jupiter is more or less where it is now. The other planets would naturally have migrated inward as long as Jupiter was the innermost giant planet. The other planets like Saturn, Uranus, Neptune, any other ice giants would naturally migrate inward and get kind of blocked by Jupiter. They couldn't migrate past Jupiter. And so they naturally end up, just like I showed for the super Earths, they end up in resonant chains where instead of being anchored at the inner edge of the disk, they're anchored at Jupiter. And they form resonant chains. And those systems are not always stable when the gas goes away. So either the gas, as it went away, could have actually rendered it unstable, or after the gas went away, the system just realized it was actually in an unstable spot without gas keeping everything in line. And then the instability is the Nice model, and then we end up with the solar system we have today. That's the general kind of picture.
Okay. Okay. So in this case, you would expect the migration to happen pretty early on,
Oh yeah,
followed by probably like the gas evaporation.
yeah.
Okay, thank you.
There is then a question by Duarte Branco.
Hello.
Hey, Duarte.
I have a question about the resonances. So in almost all of these models, the resonances are always present, but only in the Grand TAC was it mentioned that the resonances caused an outwards migration of Jupiter and Saturn. And I wanted to understand, is the effect of these, do these resonances tend to have this effect of an outwards migration, or is it specifically in the Grand TAC model because of because of some other effect?
Good question. So the way that the Grand TAC causes outward migration, I used to give talks and I would show plots of the density profile on the disk and show exactly the torque scales like this, and this is why it is. The key thing for why the Grand TAC causes an outward migration is basically the resonance itself is not important. What's important is the two planets are so close together that they share a common gap. And so basically you can think of the migration of any one of these planets as being a balance of two torques. And there's a torque from usually from the outside pushing in, and a torque from the inside pushing out. And what happens in the Grand TAC is basically there's two planets. Oh, and other key factor is the torque itself depends on the planet's mass. So it's a product of the planet's mass and then a surface density. So let's just throw out the surface density part and talk about the planet's mass. So if you have two planets that are really close to each other and they're the same mass, then they can go either way. Usually they end up going outward, usually they end up going inward because the outer torque is usually a little bit stronger. Okay, so two planets, get them close enough so they're sharing a gap, they'll stay in resonance and migrate inward. But if the inner planet is much more massive than the outer one, then the inner torque that's pushing outward can actually overwhelm the inner torque, but the outer torque pushing in, and the two planets can go outward. And that's what the Grand TAC does. And so the resonance itself doesn't matter, but to really understand the problem properly, you have to couple the conditions in the disk, which determine what resonance the planets are going to get trapped in, and basically the pileups of mass that cause these torques in the first place. And yet you have to couple that basically with the planets growing and with the disk profile. And so no one has put all the pieces in there properly together yet. So far as it's been done, it seems like for a reasonable range of conditions, outward migration can happen as long as Jupiter is basically, as long as the inner planet is 2 to 4 times more massive than the outer one. But for certain regimes, certain parts of parameter space, like very low viscosity disks, it doesn't work at all. And so it's not clear whether it really works. And no one has done this correctly while the gas giants are growing as they're migrating, because that part's really hard to do. And so maybe it can work in certain parts of parameter space, but in lots of parameter space, it's not going to work. I'm not sure if I answered your question entirely, but
No, it did. I thought the resonance had definitely more of an effect when it came to the Grand TAC model, just because it was always mentioned. But it's interesting to know that it's just a piece of everything.
yeah, the resonance doesn't matter. Just if you want to squish two planets' orbits really close together without driving them completely unstable, the only stable islands are resonances. That's why you end up with these resonances all over the place.
There is another question by Bill Irwin via the chat. Do isotope ratios, particularly deuterium to hydrogen, not constrain these models?
Good question. So these days, the constraints from isotopes in meteorites are really playing a big role. So I didn't talk about them at all in this talk, but they play a key role in terms of understanding, what Earth grew out of, the sources of Earth's volatiles, the sources of all sorts of stuff. And so yes, they play a big role, and they can constrain some stuff. But as of today, each of basically any model that comes out now has to already match more or less everything that we know right now. And so the goal is the next generation of measurements to constrain them. And so there's debates now between planetesimal and pebble accretion, whether, whether pebble accretion can really match certain isotopes that are being, measured in Earth that show a certain fraction. I don't want to go into the whole details of this, the whole carbonaceous, non-carbonaceous isotopic dichotomy and so on. But basically, the key thing is that, yes, isotopes play a key role. The D to H ratio of water, back in the day, this was kind of considered the key discriminant between like a cometary versus asteroidal source of water. My interpretation of that is that the D to H ratio is, its usefulness has gone way, way down. And the reason for that is that there's a observation of a few years ago showing that for comets, some comets have very high D to H ratios, some have basically Earth-like D to H ratios. And what they showed is that more active comets, the more active a comet is, the lower its D to H ratio, the closer it is to Earth's. And the interpretation is, this is a paper by Liss et al. 2019. And so the interpretation is basically the more active a comet is, that means that the outgassing is coming from deeper. And so it's more representative of actually the bulk contents of that object. And so what that means is that comets, their high D to H ratio is probably just the skin of the comet caused by weathering effects, hydrodynamic loss or whatever. And so based on that, comets seem to mostly have Earth-like D to H ratios. So it's not a very useful isotope in detail. Maybe if you can zoom in and get a really, really refined values, it could be useful. But in general, it's probably not the most useful isotope. But I can blab about these isotope things for a long time, so I'll stop there.
Okay, I don't really see any more questions, and also the time is running quickly, so I would like then to close here now. I just would do a quick announcement that I would like to remind you that we have got our Beacon conference in Iceland, the biannual European Astrobiology Conference from the 1st to the 5th of July 2025, where we have got 5 days of scientific program and also an early career scientists meeting just before. And there will be bursaries, and of course, we will have an excursion and a field trip after the conference where we go to boring places like geysers, waterfalls, active volcanoes, and interesting geological features. And we'll also have a conference banquet at a very nice carousel restaurant. So please tune in next week again for the talk by Ricardo Amils from the Centro de Astrobiología next week, same time, Tuesday. Thanks a lot and see you then.